Hello everyone. So, let us continue our discussion. We are in week 2 and this is our lecture 3. Now, if you recall, we derived the expression for sigma n and tau n, right. So, what is the expression for sigma n? This is sigma xx plus sigma yy divided by 2 plus sigma xx minus sigma yy by 2, then cos of 2 alpha plus tau xy sine of 2 alpha, and tau n is equal to minus sigma xx minus sigma yy divided by 2 times sine of 2 alpha plus tau xy cos of 2 alpha, where alpha is already marked here. You can see that is the angle on which this normal stress sigma n and shear stress tau n acts. Okay. And we concluded our last lecture with a question that we see sigma n, the first equation, is a function of alpha. Actually, you can see cos of 2 alpha sine of 2 alpha on the right hand side. Similarly, second equation for tau n is also a function of sine and cosine of 2 alpha. Then naturally a question comes in our mind that probably we can combine these two equations and then develop an equation in terms of sigma n and tau n, and that will give us the variation of sigma n and tau n in terms of normal stresses, that is sigma xx, sigma yy, and shear stress tau xy. That we will do. But before that, let us quickly address one question and then we will take it up, how we can combine these two equations. So, the first question today we are going to answer is how to maximize this sigma n and tau n with respect to alpha. So, let us take the first case, which is normal stress. And let us maximize. Okay. So, what we will do, d sigma n d alpha, we differentiate this equation 1 with respect to alpha and equate it to 0, right. So, if we do that, what we will get the value of alpha for which this sigma n is maximum. Now, let us first find out the expression of the first derivative of sigma n with respect to alpha. So, if you do that, obviously the first term will be 0, second term we have sigma xx minus sigma yy divided by 2 times cosine of 2 alpha. So, that will be minus 2 times sine of 2 alpha, plus we have tau xy, then sine of 2 alpha. So, that will give us 2 cos of 2 alpha. This is equal to 0. Now, if we do that, what we get? We get tan of 2 alpha is equal to tau of xy divided by sigma xx minus sigma yy by 2. So, the 2 will go to numerator. So, that is the expression we get. Now, if we look at the geometric description, what does it mean? So, we have a right angle triangle whose one side, this is tau xy. So, this is 90 degree. The base of this triangle is sigma xx minus sigma yy by 2, and if we apply Pythagoras theorem, we can actually figure out this hypotenuse. So, that is sigma xx minus sigma yy by 2 whole square plus tau xy square root of this quantity, right. Say this quantity is equal to r, right. Obviously, we can express now cosine of 2 alpha and sine of 2 alpha, right. So, what is the cosine of 2 alpha? It is nothing but base by this r. So, if we do that, we get sigma xx minus sigma yy divided by twice. Similarly, sine of 2 alpha will be tau of xy divided by divided by r. So, what we can do? We can put the expression of cosine of 2 alpha and sine of 2 alpha back in equation 1. And if we do that, obviously, we will get the maximum value of sigma n, that we will do in a minute, but before that just look at the orientation of this plane marked by this pink dotted line, and the expression of cosine and sine of 2 alpha. Obviously, between 0 to 360 degree. So, 0 degree to 360 degree, we can have two values of cosine and sine, and those two values. So, between 0 degree to 360 degree. So, let me write it 0 to 360 degree, cos of 2 alpha has two same values which are 180 degree apart. So, the first conclusion is we will get two different values of sigma n. When we will graphically present it, we will look into the meaning of this two different values, that we will see. But for the time being, we can identify that two values of sigma n will appear because of these two expressions of cosine 2 alpha and sine 2 alpha. And obviously, alpha for these two cases will have 90 degree difference. So, we will have first conclusion, two planes offering two different values of sigma n, and we have already identified that corresponding to this plane tau n will be 0. So, we write where tau n is equal to 0. So, this plane is called, it is called principal plane. So, the plane along which shear strain or shear stress is 0 is the plane where sigma n is maximum, and we call it principal plane. Okay. So, what will be the value of sigma n? So, if we put this expression, what we have, sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cosine of 2 alpha. For that, we have the expression sigma xx minus sigma yy by twice r plus we have tau xy, and for sine of 2 alpha we have again tau xy by r. Now, if we simplify this expression, what we get is the first term sigma xx plus sigma yy by 2, and then obviously the maximum value. So, let me just write it here, sigma n max will have this expression, which we can simplify. So, plus 1 by r will have sigma xx minus sigma yy by 2 whole square plus tau xy square. Obviously, we can identify this third bracketed term, this is nothing but r square, right. So, we can write down the expression in terms of r and 1 will get cancelled. So, the expression for sigma n max is equal to sigma xx plus sigma yy by 2 plus we have square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. So, that is the maximum value. Obviously, if you look at the other condition, we have actually two planes where we have maximum value of sigma n. So, the second one will be where this you can easily figure out, which is 90 degree apart, and for that we basically get max and the other optima will be where we have the negative sign of the square root. So, that is the expression for maximum value of normal stress. So, this is called principal stress. Recall, on this plane tau n is equal to 0, right. So, we have the expression for maximum value and the minimum value of the principal stress. So, positive for larger value and negative for smaller value, and these two they are 90 degree apart. Okay. So, what we can now find out sigma n max, which is orthogonal to sigma n mean. So, there are two planes along which this occurs, and for both of them tau n is equal to 0. Okay. So, now before we move forward, let us just recall we have already derived tan 2 alpha for the principal stress is what we have already derived is twice tau xy by sigma xx minus sigma yy. So, twice tau xy divided by sigma xx minus sigma yy. Now, for better understanding, let us just have a marker of this alpha. So, we call it alpha sigma n. Okay. That means, the angle alpha corresponding to principal stress. Okay. Now, let us do the similar exercise for maximum shear stress. So, what we will do in this case? We have already identified the expression for shear stress at an angle alpha. Then we will differentiate this expression of tau n with respect to alpha and then equate it to 0. So, let us do that. So, we have tau n, let me just quickly write it down. We have sigma xx minus sigma yy by 2 sine of 2 alpha plus tau xy cos of 2 alpha. So, if we differentiate this tau n with respect to alpha, so what we get is minus sigma xx minus sigma yy by 2. We differentiate sine of 2 alpha, so we will get 2 cosine of 2 alpha plus 2 tau xy sine of 2 alpha, and there will be a negative sign. So, ultimately this will be minus. Now, equate this to 0. So, what we get is tan of twice alpha, and we mark it tau n because we maximize shear stress, is equal to minus sigma xx minus sigma yy divided by 2 times tau xy. In this case again, we will have two values of alpha between 0 to 360 degree, which are again 90 degree apart. Now, we can further simplify this. So, what we have, tan of twice alpha tau n is equal to what? Is equal to minus of, if you look at this expression, sigma xx minus sigma yy by twice tau xy, and look at this expression. So, tan of twice alpha for this maximum shear is minus 1 by tan of twice alpha sigma n. Okay. So, what we can do, we can further simplify. So, here we have sine twice alpha tau n divided by cos twice alpha tau n is equal to minus, we have cosine twice alpha sigma n divided by sine twice alpha sigma n. That means, we can further simplify this expression. So, we have cosine of twice alpha sigma n times cosine of twice alpha tau n plus sine of twice alpha sigma n times sine of twice alpha tau n is equal to 0. So, if I combine this expression, what we get? We get cosine twice alpha sigma n minus twice alpha tau n is equal to 0. You can recall cos a minus b. So, if you expand this, you will get the term we have here, right. So, now what we can conclude is that twice alpha sigma n minus alpha tau n, this is equal to plus minus of 90 degree, or in other words, alpha sigma n minus alpha tau n is equal to plus minus 45 degree. Finally, what we get? Alpha sigma n is equal to alpha tau n plus minus 45 degree. So, that is the relation between the orientation of principal plane and the plane of maximum shear. So, this is the angle for principal stress and this one is the angle for maximum shear stress. And the difference between these two is actually 45 degree. So, we can easily sense the orientation. We have already figured out the orientation of principal stress. 45 degree to that is the orientation where we have maximum shear stress. It is very important expression. So, we get the orientation. Now, let us find out the maximum value of shear stress. What we have already derived is tan of twice alpha tau n is equal to minus sigma xx minus sigma yy divided by twice tau xy. We can then easily write down the expression for cos of twice alpha tau n, which is nothing but tau of xy by r and sine of twice alpha tau n is equal to minus sigma xx minus sigma yy divided by twice r. Expression of r is square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. Okay. Now, we have the expression for cosine and sine. What we can do, we can put that expression here in this equation, second equation for tau n, and that will give us the maximum value of shear stress. So, let us do that. What we have is tau n is equal to minus sigma xx minus sigma yy by 2 times, if you recall, this is sine of 2 alpha. So, we have sine of 2 alpha, that is minus sigma xx minus sigma yy by twice r, plus we have tau xy cosine of 2 alpha. So, we have tau xy by r. So, ultimately tau n, this is maximum. So, let us write max is equal to sigma xx minus sigma yy by 2 whole square plus tau xy whole square, and we can take 1 by r common. So, we will have this expression. Ultimately, what we get is this third bracketed quantity is r square. So, effectively we have r and we know the expression of r. So, the expression of maximum shear stress is sigma xx minus sigma yy by 2 whole square plus tau xy square. So, from this discussion what we get, sigma n max and min and tau n max. We also get alpha sigma n and alpha tau n, right. So, that gives us the complete expression for the maximum values of normal stress and shear stress. Now, finally, if we can address the question with which we concluded our last lecture, is that can we combine sigma n and tau n and derive a single expression? The answer is yes, but before that let us just quickly recall sigma n is equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cosine of 2 alpha plus tau xy sine of 2 alpha, and then tau n is equal to minus sigma xx minus sigma yy by 2 sine of 2 alpha plus tau xy cos of 2 alpha, right. Let us just quickly check the expression. Yes. So, we have equation 1 and 2, and what we are going to do now is to combine these two equations and see how does it look like. Before that, let us just quickly identify we have two normal stresses, sigma xx and sigma yy. So, if we take the average of these two, that is we add it and divide it by 2, we get the average of the normal stress. So, we can modify this expression. This is the sigma average. So, from first equation we get sigma n minus sigma average whole square is equal to sigma xx minus sigma yy by 2 cos of 2 alpha plus tau xy sine of 2 alpha whole square. From 2, that is second equation, we get tau n square is equal to, we have minus sigma xx minus sigma yy by 2 sine of 2 alpha plus tau xy cos of 2 alpha whole square. Now, if I add these two equations and we get sigma n minus sigma average whole square plus tau n square, and on the right hand side you see from the first equation we have sigma xx minus sigma yy by 2 whole square cos square of 2 alpha, and from the second expression what we have minus sigma xx minus sigma yy by 2 whole square sine square 2 alpha. So, the first term we will get sigma xx minus sigma yy by 2 whole square, we can take this common. So, cos square 2 alpha plus sine square 2 alpha 1. Next term will be twice of this expression times this expression, which will be cancelled because we have a negative sign here in the second expression. So, we do not need to worry about the product twice product of these two terms. The last term tau xy square will be common, then again cos square 2 alpha plus sine square 2 alpha will be 1. So, the right hand side what we have is basically this quantity which is r square, right. So, what we can write, the combined equation sigma n minus sigma average whole square plus tau n square is equal to, this is actually r square. So, we have r square. So, that is the expression we were looking at. So, this is the expression for combined expression of sigma n and tau n. What is this equation? It is a circle, and it is called actually Mohr's circle. Christian Otto Mohr, who actually derived this expression in the year of 1882. In his name, this equation is called the Mohr circle of sigma n and tau n. So, if we have a 2D stress field, then we can easily find out, we can derive this expression of Mohr circle, and that Mohr circle will give us the maximum value of normal stress, that is the principal stress, and the maximum value of shear stress along with their orientation. Now, what is the center of this circle? So, center is, if you see, sigma average comma 0, that is the center of the circle, and radius of this circle is r. So, we have already derived the expression for sigma average, which is here, and we have also derived the expression for the radius r. So, we can now easily draw the Mohr circle, and from there we can identify the orientation of principal stress and the plane where the shear stress is maximum. We will do that in our next lecture. So, let us conclude here, just go through this derivation. If you have any query, you can drop a mail to us, and then we will definitely clear your doubts, or otherwise you can also raise your question during our open session. We will try to clear your answers. So, with that, let us conclude here. In the next class, we will see how we can draw the Mohr circle from this given 2D stress field. Thank you.